Okay, so now in the third part of the video, we're going to look at velocity space. Now, what does velocity space mean? Well, basically velocity space means that when we have the ellipse, well, we haven't yet proved that it is an ellipse. So we have the orbit, and we have the focus here, which could be the sun, and we have all these velocities, which is going to be fastest here, a bit slower here, a bit lower here, a bit lower here, a bit lower here, minimum here, and so on. Yeah, when we have a point and we add all these velocities together from, or when we depict all these velocities together from this point here, and so the biggest will be here, and something a bit smaller, and a bit smaller, a bit smaller, we're going to get a perfect circle. This is not actually a perfect circle, so what I'm going to prove now is that we have something like that. The velocities will add up in the form of a perfect circle, whereby this point here is not the center of the circle because all these velocities are different. And so how am I going to do that? Well, first of all, before drawing all these velocities down, I'm just going to draw the ellipse, the orbit once again. And keep in mind that I'm not assuming this as an ellipse, I'm just assuming this as any orbit. And we have the focus here. First thing, I'm going to draw a set of lines that divides the ellipse by the same angle, by different sectors. Do they call it a sector for an ellipse? I'm not really sure of my terminology, but anyways, what I'm going to do is divide this ellipse into parts that are of equal angles in terms of the focus. So every single piece would be in the form of would be theta. There would be, I say 8 equal parts, but in fact it should be much larger. In fact, theta should be infinitesimally small. It should be d theta for it to be completely true. And if I do this, it's going to be in the form, when I link all these, it's going to be in the form of a polygon. But it's going to be easier to visualize by doing smaller segments. So this is going to be theta, this is going to be theta, everything is going to be theta. Now what did we do in the previous part of the video? Well, we established the fact that change in A over change in T is a constant, so it's proportional to 1, and which means that area is proportional to time. Change in time, just get rid of the change, we get area swept. Area swept by the object is proportional to the time taken. Okay, now what do we do here? Well, we're going to compare the time taken for the object to sweep these regions with the same angle from the focus point. Well, we know that it's going to take the least amount of time when it's closest to the focus, and it's going to take a much longer time when it goes here, because we said that area is proportional to time, and here the area is indeed much larger than the area over here. But now what do we know? Well, when we draw, let's say we draw the same, I draw the same form, maybe this part here, onto this part over here, the opposite part. well then it's going to look something like that. And I mentioned that I'm going to divide the slices up to infinitesimally small parts. And then what you see is when I divide this into infinitesimally small parts, it's going to be in the form of a triangle, because this here is going to be a straight line when I go infinitesimally small. And I don't really have to do this because it's going to work the same in the form of a part of an arc of an ellipse, but because we haven't established the fact that it is indeed an ellipse, I'm gonna use the principle that works for the small triangle. And so when we basically have two small triangles, we're gonna have two small triangles that look like this, and one triangle over here. Well, if this is the radius, they are both radiuses. I'd say that's R1 and that's R2, and that here is going to be R1. We get that this height over here, well, we say that the area over here, well, we know that if I say that's going to be H1 and that's H2, that's going to be H1 too. And what we know is that the ratio between R1 to R2 is equal to the ratio between H1 and H2, because they are both quantities that define the area. So we could imagine because they are right angles, imagine looking the triangle this way or that way. Either this could be the base or this could be the base. But basically what I'm saying is that R1 to R2 is equal to H1 to H2. And so H2 is proportional to R2. Yeah, H2 is proportional to R2. And so this means that what we get is the time taken would be proportional to the square of the radius, because when we look at here, we're basically dealing with the radius. And so here what we do is the area we get is R1 times H1 over 2, and here we get is R2 times H2 over 2. And because H2 is proportional to R2, the area is going to be proportional to the radius squared. And because the area is proportional to time, we get time is proportional to the radius. Yeah, because the area is proportional to R squared, that means that time, is also proportional to R squared. And so this is not the reciprocal, we get time is proportional to R squared. So we have A here, area, this is proportional to time, which is also proportional to R2, to the R squared. And what do we know is also proportional to R squared? Well, when we look at the equation, force is given by G, m over R squared, we get the force of gravity is also proportional to R squared, but reciprocal. So R squared over 1. Now, let's have a look at the force. Well, we define the force we define the net force as the mass times the acceleration. And so ma is proportional to R squared over 1 over R squared. We could get rid of the mass because it doesn't really play a part. So we get A, acceleration is proportional to 1 over R squared. And what do we know acceleration is equal to? Well, acceleration is equal to delta V, change in velocity over the change in time. So we get the change in velocity vector over as a change in time, say just t. I'm referring to t as the change in time, or I'd say I'll do it like that. Change in time. Here also change in time. So change in time that's proportional to r squared 1 over r squared. Which means that the change in velocity is proportional to change in time over r squared. Now, I'm going to input this into this expression over here. Here we said that change in time is proportional to r squared, which means that change in time is some constant times the radius squared. And we're not interested in any constants because there's no meaning. What we're interested is in the relationship between the variables, and we got the expression that the change in time is proportional to r squared. And so when we substitute this value r squared, which this means that we can substitute whatever is in the left or right of the proportional sign into the expression over here. So I'm just gonna substitute r squared into this over here. And so we get the change in velocity is proportional to change in time, which is r squared over r squared, which means that change in velocity is proportional to 1, which means that change in velocity is a constant. Change in velocity is a constant. We have established that fact by this triangle over here and this pie shaped over here. And so what does this really mean? That the change in velocity is constant. Well, this means that when we have, let's say we have a velocity over here, like that, v1, and then over here we have the same, but it's going to be slightly faster, v2. And here it's going to be slightly faster, so v3. Here it's going to be a bit more faster, and here it's going to be of maximum velocity, v5. That's a big dramatic change. Yeah, it's going to look something like this. And because change in velocity is constant, this means that v2 minus v1 is equal to v3 minus v2, because they're basically the changes, and v4 minus v2, 3, and so on, they're going to be same. Let's look at v1 and v2 for now. So we have v1 that goes like this, and v2 that goes something like that. I'm going to draw this somewhere here, bigger. See this, we have a point here, we have v1 here, and we have v2 with a greater velocity, something like this. And v1, v2, so it's v1, something like that is v2. It's a bit larger because it is a bit larger due to time is proportional to area. And so we get the change in velocity, the first change in velocity, that's v1, that's v2. We get that, which is v2 minus v1, change in velocity 1. That's going to be our first change in velocity. And I'm going to repeat this for everything. And here we have because we have divided the pie into 8 equal parts, we get 8 velocities. We're just going to draw what the 8 velocities are going to look like. So this part here is going to be a bit larger. This here is going to be a bit larger. And because we have said that change in velocity, and I should say the magnitude in the change in velocity, because proportionality, it only refers to the scalar quantities. So the magnitude of the changes in velocity are constant. And that means that when we draw it, you're going to look something like, it's going to be in the form of a polygon. and looks something like this. They're all changes in velocity. And you see that because the magnitude must be same and these angles must be same, it must be in the form of a polygon. And I know that I haven't drawn this perfectly, but if I take a better effort, it's gonna look something like this. It's gonna be a bit more extreme. Gonna look something like this. Whereby this length is bigger than this length, but still we get a polygon. Whereby the magnitudes of the changes in velocity, delta v, are always the same. Although, as you can see, these lengths are different. Delta v is always the same. The magnitudes of delta v are always the same. The scalar lengths of them are always the same. And imagine we take theta to the limit in terms of 0, so the small limit, d theta. You could imagine that, and you could see why that would give us a circle, which looks something like this. And now the magnitude and the change in velocity would be close to 0, but still it would look something like this. We have a circle, we have a point here, and whatever we draw, the lines, as long as the angles are constant, and in this case it's going to be 0, close to 0, very close to 0. We're going to have something like this, whereby the changes here, the length here, is not really the same, but you could imagine them being the same, whereby we have a d theta here, and then the d change in velocity over here. It's going to be something really close to a circle. And now in the next part, we're going to use this idea and ultimately prove by referring to the first derivation of how to draw an ellipse, the second part, whereby we had the perpendicular bisector. We're going to link those two concepts together and finally prove why planetary orbits are indeed elliptical using Feynman's method, in which he mentioned in Feynman's lost lecture. So on to the next part.